Okay, welcome everybody. This is Dr. DiVincenzo. We're doing a supplementary video here for Chapter 1. And this is basically designed to help those students that weren't in class on Thursday. And due to the failure of the streaming system, the video capture system, there's no video. Now, it's not meant to replace an 85-minute lecture because most of that material is contained within your textbook. It's in the slides, and it's in the video, the introductory video. What it's meant to do is kind of replace the stuff that you don't have answers to on your slides and things that I filled in kind of in the classroom. So let's take a look. First of all, is these questions were asked. Which of the above representation depicts liquid nitrogen? Well, first of all, you should know the difference between solids, liquids, and gases. Gases are spread out with little interaction. Liquids have some interaction, and solids are limited in their movement. And gases, of course, expand to the whole container. Liquids take the shape, to some extent, of that container. And then solids are kind of fixed in space. So when you're looking for that, and then you're also looking for nitrogen, you have to realize that nitrogen is a diatom. So it'd be two atoms attached together, and those atoms would be identical. So they'd have two of the same spheres. So that would be your correct answer there. Then which one would be solid dry ice? Well, you don't even have to know what dry ice is, but it is CO2. And you want to look for solid, so obviously this one would be the solid. And the last one is also CO2, but it's sublimed. And sublime is going from solid to gas, as opposed to some of the other ones you might be more familiar with, like evaporation, condensation, all those types. Sublimation is going from solid to gas. So you'd be looking for a gas, and once again, you got two oxygens bound to a carbon. Carbon's usually black, oxygen's usually red, nitrogen's usually yellow. So that's what you're looking for in these representations. So this would be the sublimed CO2. Then we looked at which of these would molecules of a compound. We're looking for a compound, which means two different types of atoms at least. Okay, and you're looking for molecules, so individual species. Okay, so that would be this one here. Okay, these are going to be arrays of atoms over here, B and D. So molecules of an element, so this would be C here. Then you got molecules of an element. So an element now, it's going to have only one type of atoms. So this over here would be your answer. And this might be like O2. Oxygen's usually red. The first one, probably something like NO. Okay. Nitrogen, so nitric oxide. Move on to another one here, a compound consisting of an array of ions. So compound, once again, you have to have two different types of spheres color-wise. Okay, so this would be D here. This one was A. And then element consisting of an array of atoms. So an element now you have, and in this case, one type of atom, but it's an array. So it's a solid array. So once again, we get B here. So this might be like maybe copper or iron over here. So that's the way you go about distinguishing these. Now I want to talk a little bit about a scientific theory. And what I said in class, one of the things about a scientific theory, most of you know about the scientific method, things like observations. Hypothesis is just a fancy name for an educated guess. And we do tests and experiments, and we do them over and over. We gather more and more data, and then it's submitted for publication and has to be confirmed by other scientists and reproduced. This is what sets science apart from other disciplines, okay? And science is really the preponderance of evidence, that collection of data that results in a statistical conclusion that draws us to the point that says, okay, well, we have enough data to say that this is fairly certain. Okay, so we have different levels of certainty. But the two things that people kind of get confused about are theory and a law. And a law is usually very specific. It often can be mathematical, but it doesn't have to be. And it doesn't try to explain anything. Think about the laws, classic laws like force equals mass times acceleration, one of Newton's laws, right? It doesn't explain why a ball has a certain acceleration based on its mass and force. It just tells you, here's the relationship. Okay, and it's very specific. It's dealing with a very specific thing. Theory, on the other hand, is broad. And it's an explanation. And when you think about the great theories, you think about evolutionary theory, Big Bang theory, quantum theory, they're incredibly broad. They encompass a lot of things. And there might be laws within those theories. Okay? And certain aspects of that theory that might be more well substantiated than others. So a theory is meant to be moldable and changeable as we get more data. It's not like you throw a whole theory out, typically. Okay? It usually gets modified to be maybe a little bit more specific. Think about what happened with classical physics and quantum theory. Quantum theory came along and said basically, well, classical physics no longer applies to things on a very small level. Atoms, electrons, things like that. Okay? But it doesn't mean the theory was wrong. It still applies to planets and balls with gravity and all of that and all of Newton's laws. That's classical physics. So we made it a little bit more specific, and we came up with a new theory, a quantum theory, and then we substantiated that over the years. Okay, so that's the real distinction I need you to be aware of. As far as the metric system, I just made a comment in class to help people that if you're converting from one of these down here to one of these up here, the number has to get smaller. That means you would move the decimal place to the left. The reverse, they would get larger. And I told people just think about comparable if you had a scale where you had dollar at the top, then quarter below it, then nickel, then penny. If you go down from dollar to penny, the number gets bigger. You go up from penny to dollar, the number gets smaller. And these exponents tell you what degree they're apart. So these two are 1,000 apart, 10 to the minus 6, 10 to the minus 9. So you move the decimal place 3 places, depending on whether you're going up or down. Okay, these were just exact and uncertain values, and obviously this one is exact. And these two then are going to be uncertain because they're measurements. We have different degrees of certainty. And that's where significant figures comes in, depending on, there's a figure in your book showing you 2 scales. Depending which scale you use, you get a different degree of certainty, a better certainty with the better scale. And then there's taking numbers that have significant figures and putting them through calculations. So we don't want to change the precision of our number. We don't want to give our number more precision than it deserves or less precision than it deserves. So we use this idea of the limiting factor, the weakest link. And when you're multiplying and dividing, it's very simple. The weakest link is the number with the fewest number of sig figs. So you only have 2 here, so your answer has to have 2. You have 3 here, so your answer has to have 3. But with addition and subtraction, it doesn't work that way. Because just imagine if you were adding these 2 numbers. You would have to report that as 3,000. Or 3.0 times 10 to the third. No, I'm sorry, 3 times 10 to the third with one significant figure. So you have to treat this as almost like 2 numbers. The whole number to the left of the decimal and the whole number to the right. So when you add these, you simply truncate wherever the one with the least number of decimal is. That's best shown right here. If we were to ask to calculate this, we'd add them up. Okay, 3, 5, since there's nothing there. 7 and 3 is 10, 16, carry the 1. 4 times 3 is 12, 13. Carry the 1, 3, 6, 9, 10, 0 down, carry the 1. 40.3653, but we got to truncate it here. So we can't go past 2 decimal places. And then we also have to round it. So 40.37, since this is 5 or greater, we round it up to 7. That's the way you report that number. So that's different than multiplication and division. Here was a conversion we did. The formulas for conversions are on your outline. The one I used in class, I think, we've got 205.43 Fahrenheit. The one I used in class was this one. You take the temperature in Fahrenheit, and you subtract 32, and then you multiply it by 5/9. That gets you Celsius. And then Kelvin, and it's degrees Celsius and degrees Fahrenheit. There's no degree symbol for Kelvin. Kelvin is degrees C plus 273.15. Okay? And I'm allowing you to calculate this yourself. We did the same thing in class. So you do the math. You say 205.43 minus 32 times 9 divided by 5 equals degree C. And I can do that real quick on my calculator here. See what you get. 205.43 minus 32 times 9 divided by, oops, got that wrong. It's 5/9. Caught my mistake. Times 5 divided by 9. Get 96.35. That's your answer for degree C. Plus 273.15. You get 369.5. Sig fig wise, we had 5 here, 5 there. This is an exact number. So you could report the zeros here. That's an exact number. We had 5. In class, I think I used only 273, so you could put 93.300 and 369.50 for sig fig wise. Because we did start with 5 sig figs, then we have nothing to limit that. All right, let's see. So that's that one. And then last, we finished up with some visual problems. We've got a faculty meeting coming up here. Homogeneous mixture. This would be saline and brass. Mixture can be solid, liquid, gas. That is somewhat homogeneous. Now, people on a microscopic level might not call that homogeneous, but usually when you talk about homogeneous, heterogeneous, we're talking about a bulk property of a mixture, not on a microscopic level, because even this on a microscopic level doesn't look homogeneous. Compounds. Pure substances that are compounds. Well, glycine is going to be a compound. It's just multiple elements here. That's an element. This is, we said, a mixture already. That's an element. This is a mixture. That's ammonia. These are all pure substances that are compounds. Okay? Don't let the pure confuse you. Just because more than one atom doesn't mean it's pure. Doesn't mean it's not pure. Okay? What we mean by pure is, it's mixed with something else. And chemically bonded is not mixed. I can isolate these things physically. Glycine, be pure glycine on a physical separation, but I have to use a lot of energy to break those bonds to separate out those additional atoms. Which contains the most atoms? Is just adding them up, but it winds up being propane. Has 11, I think, and this one only has 10. That's all. But you have to use a molecule. Okay, you can't count this because that's not a molecule. That's a mixture. Okay, and that was basically it. And there's one last thing I did at the end of class I want to show you. When you're converting something like this, and I forget what number, say I have 35 centimeters, I want to convert that to inches. And the conversion is, cubic centimeters to cubic inches. And the conversion is 2.54 centimeters equals 1 inch. A lot of people want to do this. 35 cubic centimeters times 2.54. We did this in class, dimensional analysis, centimeters per inch. You always do dimensional analysis, get rid of your units. Problem with this is that cubic centimeters and centimeters do not cancel out. So effectively, you do not have the correct units, and you have not done the correct thing. You need to cube it. Just imagine if you had a cube, you had to convert all 3 sides one at a time. So it's the same thing. You're doing it all in one step. That will give you cubic inches and cubic centimeters. These will cancel out by dimensional analysis. Your answer will be in cubic centimeters. So anytime you're dealing with squares and cubes, be careful when you do your dimensional analysis. With that, that's the video that I have to supplement for what we covered in class on Thursday, and a lot of you weren't there because of our social distancing, and this video is there to help you kind of connect the dots that are missing as you go through that material.